Hello student, welcome back. We are going to start the session Digital Image Processing. Today's session is Module 4, Lecture 7. Already we have studied the different kinds of image and their features and their structural information, image enhancement. But so far we have studied and understood that until and unless we get the exact structural information of an image, we cannot find the detail of an image. Though image can look good or every other thing is okay, but from the view of performance analysis, structural information is very important. From that perspective, edge detection is one of the important criteria for image processing. So we are going to start the session. We will start the session with little bit of previous lectures continuation, then we'll go to our main topic. Yes. So, Shongita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. This is the content of the previous lecture. It is the continuation of the lecture 6, segmentation of digital images, thresholding, segmentation based on region growing. Earlier classes we have talked about different advanced technique on digital image processing edge detection. One of them is Marr-Hilder's edge detection, that is Laplacian of Gaussian, that is to Mexican hat, also known as. This is its mathematics. It is its profile, and it is top view. It is the slice, and it is the different coefficients of this. And this is the original image and its corresponding LOG or Laplacian of Gaussian or Marr-Hilder's algorithm with standard deviation 4 and n is equal to 25. With zero crossing using a threshold of 0, then the output will look like this. But as the threshold is 40% of the maximum value of the image intensity, then it will look like this. What does it mean? That depending on our requirement, we can use this thresholding to get the exact value of the signal, what we want exactly. So as the information, we want a particular region, depending on its value, we have to, therefore it requires lot of study, lot of research, so that you can find that. Until and unless you study well, you go through it carefully, understanding will not come. It will keep on practicing, then only can what is the exact value for a particular type of application will come to your mind. Then another kind of premier edge detector is canny edge detector. Now I want to say one thing, that why we are studying this. Because it is a continuous process, you have to keep on practicing. And research is going on and in this field. So first it was LOG filter. It is good, but if there is more advanced technique, because we cannot do any absolute kind of filter, it is a continuous process. So canny is the another kind of edge detecting filter. It is another kind of step up, means it is a good kind of another filter. It is a newer filter than that of LOG filter. What is its characteristics? Low error rate, edge point should be well localized, single edge point response. Now this is its corresponding mathematical terms. Now the summarize of this is smooth the input image with a Gaussian filter, compute the gradient magnitude and angles, apply non-maxima suppression to the gradient magnitude image. Use double thresholding and connectivity analysis to detect and link edges. Therefore, one of the criteria is link edges. Therefore, There are a lot of edges are there, but you have to link it to make it the firm edges, because that is false triggering also at the time of edge detection. That is a very important point in everywhere, like any metal detection, means metal fault detection, or bone structure detection, bone crack, and everything. Lot of complications are there. So this is a image corresponding threshold by smoothing, before thresholded gradient with smoothing image, with LOG and with canny edge. Obviously canny gives more robust edge detection. In case of LOG filter or Mark-Hilder, there is some false triggering also there. This is another CT scan image. This is the original image. It is threshold gradient smoothed image. It is Mark-Hilder output, and it is canny image output. So this is our today's main topic, edge linking and boundary detection. Ideally, edge detection should yield set of pixels lying only on edges. In practice, these pixels seldom characterize edge completely because of noise, breaks in the edge due to non-uniform illumination, and other effects that introduce spurious discontinuities in the values. This is very important. Spurious discontinuities means there is discontinuities, but spurious, it is the isolated point. It may be noise, may not be noise. Therefore, edge detection typically is founded by linking algorithm designed to assemble edge pixels into meaningful edges or region boundaries. In this section, we discuss three fundamental approaches. Now, there is some local process and global process. In case of local process, we will find the small patches important features. This is the original image of 534 into 566. Now this is the gradient image. This is the horizontal connectivity. This is the vertical connectivity. This is the logical ORing, and final result obtaining using morphological thinning. This is the final output. Regional process. This is the image of a teeth. 550 into 566 X-ray image of a human tooth. This is the gradient image. This is result of majority filtering. This is the result of morphological shrinking. This is the result of morphological cleaning. This is the skeleton. This is sparse reduction. This is polygonal, and this is another polygonal fit. This is boundary detection, and this is smoothed with the same filter, smoothing filter. So you can find, you cannot get the output directly from the first step. You have to go through different steps to get the original, the layout of this structure. Lot of careful assessment should be there. Now thresholding. Because of its intuitive properties, simplicity of implementation, and computational speed, image thresholding enjoys a central position in application of image segmentation. Thresholding was introduced in the earlier section, and we have used it various discussions since then. In this section, we will study a more formal way of developing techniques that are considerably more general than what happened in previous sections. Now foundation. In the previous section, regions were identified, first finding edge segments and then attempting to link the segment into boundaries. In this section, we will partition them, and intensity values and properties of these values will be discussed. Basic intensity thresholding. So what is thresholding? There should be an image, gray image, and we should perform an operation so that a particular value should be chosen between this intensity of the image, so that above of this should be 1 and below of this should be 0, and it becomes a binary image. So this is the histogram of an image. It is a single thresholding, and it is a multimodal thresholding or dual thresholding. It may be more than 2. So this is the concept of multi-thresholding. ABC3 threshold, 3 segments has formed, and 2 threshold values have taken, T2 and T1. Some values should be below T1, some value should be in between T2, T1, and some values should be above T2. The role of noise in image thresholding. Now this is a original picture of noiseless 8-bit image. Now it is adaptive Gaussian noise with 0 min is added, and it is image with additive Gaussian noise with a standard deviation of 50 intensity levels. Now its corresponding histogram. Now this is noisy image and this is the intensity map, and these two are producted, and this is the output of these two images out of product. Now corresponding histogram is showing. Now it is a single mode histogram. This is its profile, and after this multiplication or product, this is the multimodal histogram. Basic global thresholding. As noted in the previous slides, when the intensity distribution of the objects and background pixels are sufficiently distinct, it is possible to use a global threshold application over the entire image. That indicates image should be divided smoothly, then it should be global thresholded. In most applications, there is usually enough variability between images. Therefore, there is lot of variables in the global thresholding in a suitable approach. And therefore, choosing of an approach is very important for this, and the quality of the image is very important to choose what type of thresholding we should apply. Therefore, it is a practice, it is a lot of experience should be there. An algorithm capable of estimating automatically the threshold value for each image is required. The following iterative process is showing. This is a select an image. This is a corresponding algorithm, and how to get it, the values M1 and M2 and average of these two, and this is the algorithm steps. We are not going into detail, you can study of your own. Now optimal global thresholding using Ostu's method. Ostu's method is one of the premier methods for thresholding. This is the noisy image, this is its histogram. Segment the result using global thresholding. The border was added for clarity, and this is the final image using Ostu's method. Now this method is like this. Compute the normalized histogram of the input image. Denote the components of the histogram by pi, where I is equal to 0 to number of levels, how much levels we have taken up to this level, 0 to L minus 1. Compute the cumulative sum. Therefore, Pik is equal to k is equal to 0 to L minus 1. Compute the cumulative means. Therefore, Mk is equal to k is equal to 0 to again L minus 1. The L is equal to number of intensity levels. Compute the global intensity map with mean Mg. Compute the between class variance. Therefore, Sb square k is equal to 0 to L minus 1. Obtain the Ostu's threshold k star as the value of k for which Sb square k is maximum. If the maximum is not unique, obtain k's prime by averaging the value of the k corresponding to the various maxima detected. Obtain the separability measure h star is equal to k star. Now this is the original image, its histogram. Now segmentation result with global algorithm, Ostu's method. Now global algorithm, now this is using global algorithm means one segmentation, means there is one thresholding, and using Ostu's multivariate multimodal threshold, this is used. So it is more clear. This is a noisy image, is histogram. Already we have shown how it is noisy. It is product with some noise. So it's histogram. See result obtaining using Ostu's method. Now D is a noisy image, smooth before Ostu's method. Then it's histogram. Then there is sharp two sections are there. Therefore, there is two hips are there. Then result of thresholding using Ostu's method. So output is more clear, and segmentation is very clear here. Using H to improve global thresholding, noisy image, its histogram, result obtaining using Ostu's method, then smoothing, then its histogram, then its result by Ostu's method. This is another algorithm. The preceding what we have studied, this is summarized like this. Now this is a noisy image, is its histogram, gradient magnitude image, 99.7 percentile. Now this is the image formed as a product of A and C. These two are multiplied, and this is the corresponding histogram. Then Oates' method thresholded with 134. This is another example. This is the original image of a human blood cells. Then it is histogram. It is not blood cell, I'm sorry. It is yeast cells. Now it's histogram. Then it is segmentation with Oates' method. Now it is Laplacian is done over there. Then taken histogram. Then Oates' method is performed. Now the previous, this output is again segmented using lower value to threshold using Laplacian. So output will be like this. Multiple thresholding has performed over there, and the output is like this. Now variable thresholding. This is earlier we have seen double thresholding. Now it is more than 2 levels. There are more than 2 levels are there. So threshold is more than 2. It is variable thresholding. This is the original image. It is the histogram, and output of this variable thresholding. This is the output. Now region growing. Another important topic is region growing. Now what is region growing? Say some metals are there, and inside this there are faults. How you can find this, and how the cracks are there? We cannot find this without naked eye. But if we take the picture, then do histogram, and then Oates' method or any other method, then if we connect those output, and then we can find the line, how the lines are joined and forming, and we can find the crack quite considerably, and we can do the justice for what we want. So this type of activity is known as region growing. So this is the X-ray image, this is the histogram, and this is the initial seed image, some segmentation method. Then the final seed image, this one, from this segmentation, it has formed like this. Then again it has taken another kind of operation from histogram, and different image threshold, different thresholding has operated, and corresponding output histogram is looking like this. Then again segmented, then another segmentation is obtained, then region growing, then finally this connected. See, these two, their difference. Here some points are unable to find, but here all the cracks or all the details, discontinuities are found over there. So this is a complicated process, not so easy. You cannot learn this by one study. You have to do lot of only study, but also some practical software operation, also some images, then only understanding will come. This is just for kind of information we are sharing this with you. So this is all about today's lesson. This is the reference, and thank you. This is all of the day. So we are concluding the session.